We're back again for our afternoon session, and we're really glad to have Johnny back with us to talk about debugging on the NAS systems.
Okay, thank you. Hope you all enjoyed your lunch. I'm going to talk about debugging today, and this is sort of an odd topic to have to talk about. First question: bugs. What bugs? You know, codes don't have bugs, so why would we need to talk about this? Okay, so I was trying to come up with some reasons why I'm talking about this. So I came up with 4. One of them being you might have to write some code, and what I mean by code is Fortran, C or C++, and you need to debug. Secondly, you might get some analysis code and need to debug. This is a really onerous task. I don't wish that on anybody, especially if it's a community code developed by several people. But you never know. You might have to debug. So why would you need to debug someone else's code? Well, maybe because you're getting wrong or different answers or no results at all. If you're getting wrong or different results, it could be a porting issue, not necessarily a bug. If you're not getting any results, the program could be hanging, or you're getting a seg fault or a board of some sort. So debugging can be difficult. It's for most parts an art, but there are many tricks and tools to help you to debug. So this afternoon's session is about tools, so that's why debugging is part of this afternoon's session. And lastly, I sort of wish I knew all this stuff when I was in grad school. So in grad school, I wrote my codes from scratch, nothing very long. Mind you, it's about 2,000 lines. But nevertheless, the only thing I knew at that time was print statements. So I'll just put print statements in different places to debug. That would take hours, days, sometimes even weeks. And let me just sort of share a personal story real quickly. There was one time, after having spent so much time debugging, that I finally found a print statement where if you put it there, everything worked just fine. So, I mean, I'm a very, very careful programmer. So I was just convinced that there's something wrong with the machine. And I just sort of ingest, maybe pass that to some people in the department. And then the next day, when I entered my office, my advisor played a practical joke on me. He sent a note out to everybody that I found a problem with the machine and that they should all send their output to my office. So I walked to my office and my desk was piled up, all over the place was piled up with output. Okay, so, okay. Now, before I dive right into debugging, I did allude to the fact that if you're getting wrong or different answers, it could be a porting issue. So in this little square box, I basically summarized a little bit. Porting is a topic all on itself, but I just want to mention a few points. Okay, so suppose you have a code that you download from somewhere, or you get it from a friend, or it's been running on a different machine, and you then compile and build it, and it does not generate the expected results. What do you do next? Well, the first thing you should try with, on Pleiades at least, is with the Intel compilers, there is this compiler flag -fp model space precise. Just add that compiler flag. Okay, the Intel folks have tried to make the compiler very, very fast. So in some sense, they've sometimes taken shortcuts and maybe made some assumptions they shouldn't have in your code. And so if you compile with this flag here, it will lower the optimization, and at least you might get the correct results, or at least your expected results. Another trick, which is along the same vein, is to simply lower the optimization level. The default for Intel is 02, but your makefile, so you know what a makefile is, whatever way you build the code from somewhere else, may have used 03, more aggressive optimization. So you could lower the optimization to 02 or 01. Usually 00 is too slow, but you can even try that. Third thing you can try is maybe a different combination of compilers and libraries. So on Pleiades, we have more than 30 compilers, more than 20 MPI libraries, 6 NetCDF libraries, 15 HDF. So maybe one of those combinations would work for you. Although I have to say that if you're finding problems with 2 or 3 compilers, most likely it's a problem with the code. Okay, so that's the little snapshot on porting. The rest I'm going to sort of dive into debugging. Now, I mentioned that there are several tools, and for today, because of the limited time, I'm going to talk about only 2. One of them is to use the compiler's debug flags. So we're going to spend some time with the Intel compiler debug flags. And then the second tool that I'm going to talk a little bit about also is TotalView. Okay, TotalView is a commercial debugger, and many systems have TotalView now. Okay, so
Johnny,
yes.
Before you move on, there was a question in the chat room. Can -FP model be applied to GCC?
No. Oh, I'm sorry. Yes, I don't think so. I don't think GCC has that compile option. You have to look at the man page. I know that compiler option only appeared in the last 2 or 3 years with Intel, but Intel has several folks that work closely with the GNU project, so I don't know whether they have put that in GCC. You have to look at the man page to see whether or not that option's there.
Thanks.
Okay, so in Pleiades, we typically ask people to use the Intel compiler because it's the most optimized compiler for our system. There are packages that use GCC, G4tran, and you may be stuck with that unless you know how to convert things over. So anyway, with the Intel compiler, there are 4 flags which are useful to use when you do use Fortran, and I'm going to talk about these 4 flags real quickly: the -G, -traceback, -check, and -FP0. That's a 0 at the end, not O. For C and C++, they don't have -check and -FP0, so you're limited with 2 flags, mainly these 2 flags. So what does -G do? Well, it tells the compiler to generate symbolic information, and it puts that into your .o or the object file. One of the things to watch out for is that when you compile -G, it changes the default optimization to 0. Remember I mentioned in the previous slide that the default for Intel is 02, but if you use -G, it goes to 0. Not bad, but suppose your bug occurs very much late in your run. You probably don't want to run so slowly until you reach the place where there's a bug. So you might still want to add a -02 explicitly to your compilation. Thirdly, always use -G when you're using debuggers, such as TotalView. Okay. The second flag, -traceback, what does that do? It is useful to get information about what the line number is, which routine, and which source file, okay, the bug occurred. So this is what the -traceback would do. So, okay, I see the minus sign just sort of missing on the board over there, but there's a minus sign in front of the traceback there. And what you see in the output here is there's a bunch of unknowns. Those are system libraries you don't have information on. But then the ones which does have information, it says from line 13 of your main program, that called subroutine sub1, and the aim subroutine sub1, which is on line 24. So basically, there was a floating divide by 0. This is what this would tell you. Okay, so it's a very useful thing to get to be able to debug. Okay, so third one, -check. -check, if you just use that flag all by itself, it's the same as using -check all. The -check compiler flag checks for many things. The 2 most useful ones are checking for array bounds and checking for uninitialized variables. Okay, so let me talk about the first one. If you check for array bounds, which if you just want to limit to checking for that only, you could use -check bounds, which I have in my parentheses there. So what is that? Suppose in your code you dimension an array to be A of 100, and the code starts using A of element 101. Okay, that's you've basically got an array bounds violation. Now this is very common. This is what we call what we call the off by 1 error. Okay, so lots of codes, they have things such as just the boundary points may be the ones that you go over the array bounds. It's a very, very common error, and -check bounds is useful to catch those. The second one is you might have a variable which has not been initialized. and you're using that. And sometimes, if you're lucky, that happens to be 0. You may never catch it. The caution that I put here is that the Intel's checking for uninitialized variables is very limited in scope, and in my example, I'll probably show that. All right, and last thing which I have in red is that after you finish debugging, make sure that you leave out this -check flag, because you make a program run very slow. Okay, so the last flag to talk about is FPE0, that's floating point exception. This is where you want to trap things like divide by 0, square root of negative numbers, and so on. Okay, by default, you just get what's called nans, not a number, and the program just continue running, generating nans. But so if your output has nans in there, this is a compiler flag to use to find out where you had a floating point exception. And the other point I want to make is that if you compile with -fp0, make sure that everything, all of your source code is compiled with that compiler flag. Because what the Intel compiler does is what we call branch speculation. So again, I have an example here with an if statement. So if z is not equal to 0, then you can do y is equal to 1 over z. Otherwise, you do y is equal to 1 plus z. What the compiler actually does is generate code so that during runtime, both branches are evaluated at the same time. And then once it figures out which branch to keep, you throw the other one out. Okay, and you might get false positives because it's calculating the 1 over z when z is 0. Okay, so what I want to do next is, let me just show this real quickly as an example of a array bounds violation message. So this is a severe message. FORRTL just stands for Fortran Runtime Library. This is a severe error where it caught that the subscript number 1. So my array could be a multidimensional array, but it's telling me that the first dimension, subscript number 1, it found a value of 101 when the upper bound was 100. Okay, so this is what the bug would look like. So what I thought I'll do next is start going to my demos, just sort of show you some of these flags in action here. Okay, so I have a program. How much time do I have? I think I'm going slower than expected, 12 minutes already. Okay, so let me just go through this program real quickly and just show you what's in there so that you can see the sort of bugs I put in there. I've got a couple of arrays, A and B, which are dimension be 100, and then C is another constant, okay? And the next two statements, A is equal to 2 and B is equal to 3, is just Fortran 90 syntax where I'm setting all elements of A to 2 and all elements of B to 3. So when I print A of 1 plus A plus 2, that should be 2 plus 2, and I should get 4, and B1 plus B2 should get 6, right? The next statement, this is a bug, right? So I've got B3 is equal to A3 plus C, but nowhere have I defined what C is. So I should be able to catch this as a bug. Now, once I pass this into my subroutine, okay, I'm passing the arrays A, B, and then scalar C into my subroutine. Okay, let's take a look what's in the subroutine. The subroutine, okay, I put in the dimension and I do another thing where I do Y3 is equal to X3 plus Z, where Z is my C value that I passed in. But remember, I never defined what C is. So this is another bug, but I'm going to show you that the check doesn't catch this bug. Okay, I've got to divide by 0. Okay, so Y4 is equal to 1 over 0. And then this do loop here, notice I'm going to go from index 10 to 200, but my array was dimension 100. So I have array bounds violations. So I've got some bugs in this code here. Okay, so let's see what we can find. Suppose if I didn't compile those compile flags and just try to run it. Okay, and okay, so well, the first two came out okay, and then but after I call subroutine, notice that B1 plus B2 now has a wrong value. Plus, looks like my job's hanging as well. Let me try Control C out of this. Okay, so Control is not working. How about Control Z, suspend that. And let's see, I'm going to try and kill this thing. Buggy. So we have, okay, let's see, this is PID. When you have a bug in code, the behavior can be non-deterministic. Okay, now I'm going to start the exercise of debugging this with adding those flags in there.
John,
Yes.
We discussed the kill. I did the same thing before we started because I wanted to see what
Yep, yeah.
I just Control Z that I didn't kill. But is that a problem?
They still run in the background. It's just suspended.
So PS is how you do it.
PS minus C, capital C, the name of my command, which is buggy, and then I wanted to find out what the PID is, so I grab that. Okay, the kill command is showing up now. Okay, so I've just finished compiling that, and the very first thing that I find here is that it's telling me that this variable C is being used without being defined, line 11. So line 11 is this one here. So for right now, I'm just going to comment it out. Okay, so this is the way debugging works, right? You're just basically going to have to correct your bug. Doesn't find them all at the same time. It finds the first one, and the job basically dies. And then you have to then get rid of that bug and find the next one. So the next one says I've got a floating divide by 0, and it's showing that it's a line 24. And so if I look at line 24, is this divide by 0? But notice that it didn't catch this one here, the line before, where I added the undefined variable, right? But it caught this one here. So I'm going to also get rid of this bug just by simply commenting out. Let's see, I think I didn't recompile. Here it is. Recompile that. And now I found the next bug, which is the array bounds violation on line number 27. Okay, so if I look at line number 27, you can see that this is the inside of do loop where I have gone over 200. So finally, if I just change this back to 100, I mean, there's various ways to fix this. Oof. Recompile, and I think that should be all the bugs in there. Okay, all right. So this is an example where I just went through a process of getting one bug out after another. Okay, so let me actually want to use this a little quicker.
There are a couple of questions you might want to take care of before
Okay.
moving on. So Eduardo asks, there must be two versions of the system lives, debug versus non-debug? Does that make any sense?
System libraries?
Yeah, I don't know what context that is meant in.
The,
MPI, he says.
Oh, MPI. We're talking about MPI, which I haven't gone into yet. We have just basically one set of MPI libraries. We don't have an MPI debug library, if that's what you're asking about. As far as system software, that's also, if that's part of the operating system, there's only one set. So you basically stuck with that. I wouldn't jump into trying to debug the system library or the MPI library. So the only parts that you care about having a debug version is of your own code. Okay?
And then the next question is, because there is no check and FPE0 options for C and C++, are those options assumed by the compiler or not?
They're not. C programmers are a different breed. Unfortunately, the compiler is not able, or at least Intel did not put that capability into the C compiler. The Fortran, they typically would dimension arrays somewhere at the beginning so that you have some predefined array dimension, but in C there's ways to program where you have linked lists, for example, you can extend the linked list and so on.
Right, often the array bounds aren't known in C programs, so
Yeah.
to the compiler, so it wouldn't be very effective.
Right. So I don't know if people heard Bob mention that for many C programs, the array bounds are not known, so that it wouldn't be useful to be able to debug that. Okay, so let's see. The take home of this demo, and I have like 4 demos. Okay, is that these compiler options are useful for catching most common bugs, but not all bugs. So a code that passes a health check just with the debug options does not mean that it's bug-free. Okay, so that's the take home for this this one here. Yes.
Is there any way we can fix all the bugs at the same time, or at least several?
No, because these runtime errors, as soon as the runtime library detects an error, because you've put in these checks, it will stop the program right away. So it's one of those iterative things. You find the first bug, and then find the next one. And let's see, a couple of things that I didn't show in this example, but I want to just move on. But I should mention right now is that in Fortran, especially legacy codes, you may find that in subroutines, when arrays are passed into it, that they don't pass the whole dimension. They just say this is the array, because all they need is the address of what we call the base address of the first element, A of 1. Because in the routine itself, if you do A of 100, they just do an offset from A of 1. So many times in subroutines, you may see arrays dimension with a 1 or star. And in the past, this caused problems, because with dash check, it would say, hey, your array is dimensioned with 1, and you're using element 2. So Intel changed that. Okay, now it no longer traps that. It just says, oh, you dimension 1, fine, we won't check anymore. Okay, so array bounds checking becomes ineffective if you have things dimensioned 1 or star. Okay, so another reason why, just because the code passes these health check doesn't mean it's bug-free. Okay, a second example, let's see. I'm going to try and go through that quickly also. Let's see. It's actually a real case scenario that I saw a few years ago, and let me just sort of go through this program real quickly for you. Okay, so what I have here is a very simple program where I have 2 integers, and m is set to 5, n is set to 7, and I'm going to pass these 2 integers in. Now, in the real case scenario, what the user had was a really complicated routine where they wanted that routine to do something, so they passed in a logical variable. Okay, this logical variable is true. Okay, so what does this routine do? Okay, it takes my m and n, and they want to do this routine only once. So if it comes in as being true, they're going to set k is equal to m is equal to n, and n is equal to k. You know what this does, right? It just switches the variables m and n. Okay, so k is going to be a temporary variable. It's going to have the value of m. M is going to take whatever n was. So m is going to have n, and n is going to take the value of k. So what I've done here is just switch m and n. Okay, and I only want to do this once, so I'm going to set my flag to false. And then in the other routine, print, I'm going to I want to print something. So if the flag is true, okay, if it's true, I'm going to print m, and if it's not true, I'm going to print n. So what do you think this is going to print? Take a guess. Okay, so m was 5 and n is 7. After you switch them, what is this supposed to print? It should, yeah, because I'm telling it to be true, right? So m should be equal to whatever you've got switched to, and I believe it should be 7. Okay, so let me actually copy this program here, because I think it's a more effective okay, so I'm going to my old machine here, Columbia machine, and I'm going to compile that. It's called the executable TV. It takes longer to compile on Columbia, but it should come back pretty soon. So if I run that, see, it shows n is equal to 5. And if I use a older compiler, okay, so I do a module switch. So you're learning some module commands along the way. If I switch from this version of the compiler to a older version, so I've got a 10.0.026, a version 10 compiler, and I recompile that, okay, and run this, I get a different value. Okay, so different compilers gives different answers. Let me go back to Ladies, and let me see what I have here. Module list, and I'm going to do a module avail compilers. So I want to show you what happens if I module load. I'm going to load a PGI compiler. I'm going to use the latest and greatest PGI compiler. But before I use the PGI compiler, I actually didn't do this on Pleiades yet. So let me show you what happens if I run this on Pleiades. It dies with sec_v. Okay. So I've got a program here that it's called sec_v. But if I compile with the PG-F90 compiler, let me just say PG here, just to distinguish this. Okay. The portfolio group compiler gives me a 5. Okay, so I've got things all over the map. I've got m is equal to 7, n is equal to 5, and let's take a look at the program one at a time. Okay, so how could this be? Okay, I've switched m and n. Okay, and then I'm telling it that it should be true, and so it should be printing m. So why is it printing n? Okay, so what's happening here, and this you may have gotten a little bit of a hint from Intel, is that right in this statement here, where I set I flag to false, what has happened is true, and I have a memory location that stores true, but everywhere where that location that location which contains true now has false in there. So every time you use true, it actually is false. Okay, so that's the reason why this happened. If you have, I won't actually run this one here. Here's another example here. Integer I and j, and once you grow old like me, this is supposed to be I, j that I'm passing in, but I looks just like 1 and L. They all look the same to me. So I've got a typo where I'm passing 1 in here. And in this subroutine, I said I is equal to 5, j is equal to 7. Okay. So what has that done? What it has done is everywhere in your program where you have 1, it now contains 5. So if you call subroutine 2 and tell it to print 1, so you can run this and just show that 1 is equal to 5. Okay. So what are the take homes from this demo here? Well, bugs can cause different results with different compilers. Okay, we saw that, and even on different machines. And just because you get the same results, okay, remember on Pleiades, if you use the Portland group compiler, you got the same answer as the older Columbia. Doesn't mean the code is bug-free. Okay, so those are the take-home from here. Okay, I have 15 minutes. Okay, so the next tool to look at is total view, and I'm going to try to just give. Anybody here have used total view before? No one's used total view. Okay, so total view takes a long time to show, but I want to show just a little bit about the power of total view. And what I want to show here real quickly is just some instructions that you're going to see me do, and that is you log in to Pleiades with X11 forwarding turned on, and you can echo dot display to see that you have something set there. Okay, and to use total view, you have to compile with the -G compiler, and I'm going to submit a PBS job, and the environment variable that I want to pass is this display environment variable. This is what allows GUIs, X11 GUIs, to display back to my laptop. Then I'm going to load the total view module and start up total view with this npexec command. Okay, so let me actually do that. So q sub -i, and I want to. So let me just show you what my display environment variable is set to. Okay, it's set to some value here. So q sub -i interactive job. Let me pass this display environment variable to my PBS job. -q devel at PBS PL3 -l select. Just pick one node. Okay, I'm going to pick that. Okay, so my job is started. And let me take a look at what I've loaded. Okay, so let me just load the total view module. Okay, let me get rid of those core files. I don't need those core files sitting around. And I'm going to compile another program. This is called SumBuggy. This is an MPI program that does basically a sum of squares. I want to -g and link to the MPI library. So this is an MPI program. So if you have MPI programs, typically you want something more than print statements, typically, to do debugging. And total view is the usually debug of choice. Okay, so I start with -tv. Let me do this, say, with 12 processes. Before I do that, let me just actually run this. See what's happening here. Okay, so when I run, what I see here is that my program hangs. Okay, I've printed out partial sums where each process is adding their portion of the sum. And don't worry about the 811, just something I added to the program. But the important thing here is that this is a program that's hanging, and I want to do some use total view to debug this. So okay, so I'm going to launch the total view debugger. It opens up some GUIs. Okay, so this startup parameter here, it allows you to put in arguments, command line arguments. If you have standard IO files, you can put those in there. For this program, I don't have anything that I need to add. And so I'm just going to click OK here. So in the main window, I'm going to hit Go to start. And total view tells me this is a parallel job. Do I want to stop now? It says yes. And you can see here, this is my program, which is basically adding sum of squares. At the beginning, we have the typical MPI initialization things. And what you have here on the left column, a bunch of squares where you can set breakpoints. I'm going to set a breakpoint at line 20, where each process is going to accumulate their local sum. Okay, and let's go ahead and run to that. And what I wanted to show here is that some of the features, instead of putting print statements, I can use my right mouse button in my mouse and print across all the processes. So that should open up another GUI with the value of the local sum on all the processes. And right now, they're all 0 right now because I haven't actually executed this line. You can actually step through this program using either next or step. So after clicking the next, oops, let me just close this window, I don't need that. You can see that each of the ranks has their value of the local sum. Since I've only gone through this loop once, rank 0 has 1 squared, rank 0 has 1 squared, rank 1 has 2 squared, and so on. Okay, and you can, let me just move this to the side so you can see, you can sort of just step through this, and you can see that value changing for all the processes. Okay, the difference between next and step is that step actually will step into routines. So if you have a subroutine call, you step into the subroutine. The out button here allows you to step, after you've looked enough at the routine, you want to run out of the routine, you can hit the out button. Okay, so at this point, I'm going to get rid of the breakpoint and just let it continue running, because I wanted to find out why it's hanging. And there is a bug that I introduced into this program, and it should have finished running by now, but it's still running, so I'm going to click halt to see what's going on. And sometimes this isn't quite exactly what I expect. Okay, so what you can do here on the buttons down here, the P plus, P minus, allows you to scroll across the different processes. Okay, and I started this out with 12 processes. Up on the top, in the sort of below the menu bar, you can see which rank I'm looking at. This is rank 1. And if I click back on my program, sum of squares, you see that rank 1 has already gone to MPI finalize. But where's my rank 0? Let me go to P minus, expecting this to show. Okay, so sometimes the problem using debuggers like TotalView is that they don't quite perform the way you expect. And this time here, I wasn't able to show you where rank 0 was, but in my previous test of this yesterday, it would show that it's all at MPI receive, waiting to receive. And the bug, which we can see with rank 1, it's in here. Okay, let's just show you this little piece of code here. If my rank is 0, this is the place where all the processes are going to send a local sum to rank 0. And I'm going to loop over all the ranks. Okay, so it starts with, I didn't need to put my rank here because my rank is 0. So this really goes from 1 to n size minus 1. It's basically going to receive from all the other processes. And so I'm going to receive from div process I, and the tag I'm going to use I also. The send, which is what all the other processes are going to do, they're all going to send to 0. And the bug here is that I also use the same tag I. Okay, and the reason why that's a bug is because in this do loop that rank 0 is doing, it knows what the value of I is. This sender done by all the other processes, they're not inside a do loop. But it's a common mistake, right? I just sort of mirror my receive and send. Since it has a tag of I also put a tag of I here. But I here is undefined. What I really should have put here instead is my rank, right? So the other processes are going to say my tag is my rank, and the receiver is going to match that tag over there. Okay, so I think with that I'm going to stop TotalView and just mention that TotalView is a really powerful debugger, and that if you find yourself spending lots of time debugging, that this is a good debugger to learn.
And James Wang asks, is TotalView useful for serial and OpenMP programming also?
Yes, it's also useful for both. And you launch that with just TotalView and name of executable. So you can do serial, you can do OpenMP.
And someone else asks, how does TotalView know where the source file is located? I assume it's in the same place with the executable?
Right. I didn't show that part, but in the several pull-down menus, the first menu there with file, there's a search path, and you will open up a window where you can put in all the directories for where your source file is located in. Okay, but the easiest thing to do is put everything together in the same directory as your executable. So if your source files and executable are all in the same directory, you'll find all of that without you having to enter all that information. Okay? All right, so let me just point out that in my slides here, I give a couple of links to the references on using TotalView. They also have several videos on the website where you can look at their tutorials on using TotalView. Okay, right. So last slide, last demo. this is actually my last slide. I'm going back to something that you guys love, hate again. Going back to high school, okay, and here's another problem, okay, and that is, what is the limit of this square root as x approaches infinity? Okay, now, you take a high school calculus, you probably know how to do this problem. So let's see, how many people know the answer to this? Okay, suddenly when x gets very large, you have infinity minus infinity, right? So that's probably 0. But the first term there has a 3x, and the second term has 2x. Well, maybe the first term's a little bigger. So since we don't have a high school student here, let's write a program, right? We just put larger values of x and see what the program tells us the value is. Okay, we've got a computer, so let's write this program here. So I've got already a program written where I just, to make it a little interesting, I changed the value of 3 to 3.248, just a little more complicated here. So what is this program doing? Okay, I've declared x and y, okay, and I set x to be 1, and y is going to be that term there. Instead of square root of x squared plus 3, I'm going to use something a little more complicated, 3.248. Okay, just so that I have a few more significant figures. Minus square root of x squared plus 2x. And another way of calculating this that you may think, what we should really do is factor x out. But I'm counting that out right now, but I'll do that example next. If you factor x out of the square root sign, then the first term is just going to be x, right? And this second term here, because you factor x out, this should be divided by x. Same thing on this side. Okay, that's commented out. And I'm going to print the value of x and y. And then I'm going to loop here just by incrementing x by a factor of 10. So eventually it's going to go from 1, 10, 100, and so on. Okay? So if I compile this program, I4-O xnth, and just run this. Well, let's see. So I print the value of x and y. So here's x. And the value of y, well, it looks like, let's see, it's going to some value, maybe 0.624, maybe 0.6235. Hey, well, here's an answer we do like, 0. Okay, infinity minus infinity, 0. So what answer do you think it is? Well, let me go back to the slide, because I think this is, well, let me actually do the other example. I'm sorry, here, let me just VI this file. Maybe the other way of doing this would be better. So let me comment out this thing. Okay, so the problem here is I've got infinity minus infinity type of term. And, oops, and, okay, and I'm going to uncomment the second one. The second is going to have the same problem though, except that when x gets very big, this term is going to get very large, and what you have here is basically square root of 1 plus something close to 0 minus square root of 1. So you got some term that's infinity times 0. That's going to also have a problem, right? Yeah, that algorithm calculate this also doesn't really help very much. So having a computer to calculate this is not really helping us, because we still don't know what the correct answer is. But has somebody figured out what the answer is already to the problem that we had before? Okay, so let me actually motivate this. If your calculus teacher was here, what they would tell you to do is, problems such as these, you're supposed to multiply this by 1 with a complement, which is a square root of this thing plus the square root of the other thing on top and bottom, okay? So if you multiply by 1 that form, what do you have on the numerator? The x squared is going to cancel, right? Because you're going to square that. And then you have a 3x plus minus 2x. So the numerator is going to be just x. And the denominator is going to have the sum of these two things. So you basically have x on the top, and the denominator you have something on the order of 2x. Okay? So the limit as x approaches infinity is this limit goes to a half. Okay? And for my program, that I had there, instead of 3, I had something a little more complicated than 3. You can calculate that in your head also. Okay, so what is the message here? The message here is that I used the wrong algorithm to calculate this. If I had used correct formula, and since I have 1 minute, so I won't actually do that, but I'll leave that as an exercise. If you change to the correct formula to calculate this, you get correct answers all the way to a large X. Okay, so what point am I trying to make with this demo here? So what is the issue here? Is this an issue with round-off error? Or is it an issue with improper algorithm? Okay, so we're not going to agree with this, so I'll just leave those as rhetorical questions. The other points I want to make is things such as sensitivity analysis. This is something that in many fields people do sensitive analysis. I'm not sure how many codes in earth science contains this, but really the question you're asking is how sensitive are the results to uncertainties in the model parameters, your input data, measurement data, and so on. Okay, so this is a field in itself. Another term that I wanted to mention was this thing called butterfly effect. I think maybe Jennifer knows what butterfly effect is, but I'm not sure if anybody else has heard about the butterfly effect. Okay, I hear some people nodding here. Mm-hmm. So it's different from round-off error. There are problems which are chaotic. Chaos theory says that if you have 2 points which are very, very close together, but not exactly on each other, that over time, they're going to go to completely different locations, okay? And it could be that the system you're modeling, the weather, could be chaotic. And little errors such as whether you take into consideration a butterfly's flapping of the wing could change whether you have a tornado somewhere else. Okay, something interesting to Google. This is a term that came out from meteorology. And I think, let's see, last question here was, what is the difference between non-determinism due to chaotic systems versus propagation of round-off errors, which you have to sort of live with, right, with programs. So anyway, I think that's the 4 demos that I wanted to touch. I think you also might cast a poll on all the positive things that you've been hearing this week, that you've got all these great programs that can do all these fantastic things, and the lesson here is that you may have to take it with a grain of salt. And I know that there may be people listening in to my presentation, and if you have lots of programs, I want to make it clear that this talk here, in no way am I saying that your programs have bugs. I learned my lesson in graduate school a long time ago, so please don't send me your programs.
Thank you very much, John. Seems like the chat room questions have been taken care of. Any other questions for Johnny right now?
Yes.
Yeah, it seems like the correct answer for the code over here on the last demo here should be 0.624.
Correct.
But as we can see from the results, that when x equals to 1 times 10 to the 16th, the value exceeds the number.
Right.
So what's the problem thing?
That part is round-off error. So basically, what's happening here is that in double precision, basically the number of signal figures that you can have is around 16. Okay, so when the first term here, x squared, and the second term, 3x, differ by more than 16 digits, you're going to start losing signal figures. So that was clearer if you factor the factor of x out. Okay, so that your first term is 1 plus 3 over x. You can see that when x goes to 10 to the 16, okay, that those 2 terms, 1 and the 3 over 10 to 16, are going to start differing by 16 digits in terms of, it's going to be 1.00000 all the way to a 3 at the 15th place there. And then if you keep on dividing by 10, you're going to start losing that 3.
Okay, well, with that, I think we need to move on to Dan Cochran's presentation. Should we stop for a moment here, Mike, just to transition?